The series comparison test is very simple to state and makes a lot of sense, but unfortunately is sometimes a little bit tricky to use. What it says is suppose I have two series, an A series and a B series, and that all the terms of the A series are smaller than all the terms of the B series. We'll take both AN and BN to be positive numbers. If you have some negative numbers, just take the absolute value. Now, since the A series is then smaller than the B series, if the A series diverges, then the B series, being bigger, also has to diverge. In fact, they'll both diverge to infinity. Conversely, if the BN series converges, then the AN series, which has to be smaller, also converges. Now, caution, this test does not tell you the values of the series. So if you want to find the actual value, say for instance, you found that the AN series converges, you will have to find that some other way. This test won't tell you. It will simply tell you that it has a value, and it leaves it to you to figure it out. So as an example, let me give you an example. Let me give you, in fact, two examples. So let's consider the series. Here's a series, and I want to know, does this converge or not? Well, if you look for large values of n, this looks like n over n cubed, or 1 over n squared. You could use the integral test to find out that 1 over n squared, that series, converges. So let's see if that tells us anything here. Well, one thing you could do is, if I look at one of these typical terms, notice that the 4 in the denominator there, if I get rid of the 4, it makes the denominator smaller, so the fraction is larger, which is to say that we have this sequence of inequalities. So in particular, if this series, 1 over n squared, converges, then this series converges. And indeed, this series does converge by the integral test. So yes, this series converges. Now let's take a similar looking series and ask, does this series converge? The only difference between this series and the one we just looked at is the 2 in the exponent in the numerator. Okay, well, we could do the same kind of thing. And get rid of that 4 in the denominator, we get something bigger. And so we could write a similar statement that we had just a moment ago. So if that series of 1 over n converges, then we know our series converges. But in fact, this is not true. This is the harmonic series. It diverges. So this particular comparison gives us no information. So the comparison test fails. No conclusion. You cannot use a comparison with 1 over n with this series to find out if it converges or not. That seems kind of bad, but in this particular case here, we can compare it with a different series. Let me show you how that goes. So we want to study this series, and the comparison goes like this. What you should notice is that as n gets large, n is bigger than 1, this series, the terms are always bigger than these terms. Notice what I've done is I've added an extra n cubed multiplied by 4. That makes the denominator of this fraction bigger, which makes this fraction here smaller. Okay, but having done that now, notice what I've done. I now have a common factor of n cubed in the denominator. Okay. Now, this is a multiple of the harmonic series, which we know diverges. So, since this multiple of the harmonic series diverges, our series is bigger than this. So our series diverges too. So this is just a quick example of how you can use the comparison test to figure out whether series converge or not. The tricky part in every case of application of this particular test, the comparison test, is figuring out what to start off with, i.e., what do you compare with? Truth of the matter is, there are no hard and fast rules. You'll just have to play around with a bunch of them until you get some intuition and some feeling for what you should compare with.